All right, let us do the section 1 for Physical Sciences 3, and we will be talking about not quite electricity like this, but electric fields and the like, and that'll get you to electricity soon, but we got to get pumped. So, electricity. Um, our first question for you to answer is true or false? The electric field is the same as the electric force. Are these two the same things? And I will give you a second to think about that. All right. So, the electric field is usually written as an E, a little arrow over it. The electric force, F with a little arrow over it. And maybe you want to do, put a little Q or a little E down here to say electric. You could say electric. And the answer is these two are not the same. This is false. And there's actually a relationship between the two of them. The force on some charge that has a charge of Q, the force on that in an electric field, E, is just Q times E. So Q times E equals this force electric. And so they're not equal, but they are related. All right, next question. True or false, an unknown configuration of charges, so I'm not showing the charges here, but an unknown configuration of charges is creating this electric field. So in green, I'm sort of showing you an electric field. And then we put a positive test charge somewhere in the field. So let's just put a little positive test charge. So that's something like, right here is a little plus. And it's small little charge. It's not affecting the field too much right there, around there, but it is in there. And now the question is, the force on that test charge, is that in the same direction as the field at that point? So for example, this test charge, the field at this point is going sort of up and to the right, like kind of like this arrow right here. So is the force on that little positive test charge in that same direction? The answer for this one is true. So the force on the test charge is going to be indeed in that same direction as the field right there, and that is because of what we just said before, which is that the force, the electric force from that electric field is equal to Q times that electric field, and we just have some positive little number here for our test, the charge of our test charge, but the direction which of the electric fields, that is going to be the same as this, because this is just like, multiplying by like 0.0001 or, multiplying by 0.2 or something like that times this electric field, which already has a direction. This number cannot change the direction of that when they're multiplied together, so we get the same direction for our electric fields. Now, if we didn't say positive, instead we said negative charge, then this would actually be false, right? Because if you had a negative charge right here instead of a positive charge, then that negative would mean that the vector is going to point in the opposite direction for the electric field, because you have a direction, up and to the right here for your electric field. Put a negative number in front of it, then you get that negative vector pointing in the opposite direction. So it'll be pointing sort of down and to the left right there. So, question, is it possible for an area to have an associated vector? So true or false? An area, and I'll just draw an area for you, something like this little area here. Put a little a, put a little a there. Does this have an associated vector? So it's true. you can have an associated vector. So the vector is the area vector, which is denoted A, little area over it, and the magnitude of A is equal to how much area there is right there, and the direction of it. So this direction is perpendicular to the surface. Okay, Gauss's law, right here, Gauss's law only applies for a Gaussian surface of a certain type, right? So you couldn't just choose any surface you want when you want to use Gauss's law. You have to choose a very specific surface. Like, so let me just give you an example before you go and you figure this out. So let's say we have, or let's do this, make that a negative charge actually. So we have like a negative charge here. We have another negative charge here. Maybe there's a positive charge right there. And then you just draw a random like surface like this. Right? And so I'm just trying to draw sort of like my surface has like, there's like weird contours in it. So I'm just trying to show you that it's like sort of a 3D surface. So true or false, Gauss's law only applies for certain Gaussian surfaces. So it wouldn't apply here. So is it true that it would not apply here? This is indeed false. You can always draw any surface around charges, and that is going to be a Gaussian surface for which you can apply Gauss's law. The only problem is that it's really hard to use Gauss's law here because Gauss's law involves you doing an integral of the electric field dotted into the area vectors. And there's a bunch of, very like all the area vectors. Like, so here's a little area vector here. There's an area vector up here, and these are all pointing different directions. And it's really hard to just write an equation for all those different areas. If you instead, you had some very symmetric situation, like you have a cylinder like this, and there's the charge, like so we'll do this later in the section. Just imagine like a line of charge that's going through here that has like some positive charge all along it. Then you can do this integral fairly easily, because if you imagine writing the different variables in here, the different coordinates in, say, polar coordinates, you'd pretty easily be able to integrate along this angle for a fixed radius. So, you could sort of imagine if you're doing, or cylindrical coordinates rather, you could do this integral. And by the way, just by symmetry, you might just be able to see that the electric field is the exact same size everywhere on the cylinder, because everywhere on the cylinder is the same distance from this line of charge. So you're sort of taking advantage of symmetry when you use Gauss's law, even though you could always use Gauss's law if you were able to do this integral for the crazy surface. All right, true or false? If there is no electric flux through a closed surface, this means there are no charged particles in the surface. So let's make this easy to picture. So let's say you have some closed surface, like I'll draw a sphere here, something like a sphere. And I'm not going to tell you if there's any charged particles inside, right? I'm just going to tell you that the flux, which we can write as this, right? So we usually write flux as this symbol right here, that capital phi, which is the integral of the electric field dotted into the area. So if this, we're just going to assume this is equal to 0. So does that mean that there are no charged particles inside? So true or false, there are no charged particles inside if this is the case. Okay, so this one is actually false. If this were to say there's no net charge inside, that would be true. But it's possible for you to have, say, a charge that's, say, -1 coulomb, and you have a plus charge in here, which is +1 coulomb. And this would lead to a situation where you indeed have no flux, but there are some charges inside. But and the equation is that for this that you can still have zero flux even though there's charges inside, is the equation that says the Q enclosed in a Gaussian surface over epsilon naught is equal to the flux. And if the overall charge enclosed, the net charge enclosed is zero, then the flux is zero. All right. True or false? The electric flux through an area depends on the electric field through the surface, the area of the surface, and the angle between the two surfaces. So the answer to this is true. And this is just an expression that is describing the integral for flux. So our flux, written as that capital Phi, is going to be E dot dA. And so the E part is going to be the electric field that's going through that surface. The area that we're going to do the integral of is the area of the surface. And the dot is a dot product that says how aligned are these two angles. So I know this is kind of abstract, so let me give you a little picture here. So if we have some area here, size is A, and then we have an area vector coming out. We said that areas can have vectors. And so we have an area vector there. And then there's an electric field, and the electric field is going through the surface. So let's just draw this electric field that's going through our surface here. That is going to be E. But these aren't perfectly aligned, right? There's some angle you can see, right? So here we have our electric field. Here we have our our area vector, and electric field. And if we zoom in, there is some angle here like theta. And we'd have to do, so if we do the dot product between the two of these, and then multiply the magnitude of the electric field and the area, then we would get the flux. So the magnitude of each of them matter, as does the angle between them, in order to get the flux. All right. This one is asking which of the following statements about electric field lines is incorrect. All right. So field lines begin only on positive charges and end only on negative charges. The density of field lines indicates the magnitude of the electric field. And the last one is field lines may cross each other. So you can get field lines crossing each other. And then D is just, they're all correct. So take a second and think about that. Okay, so let's go through these one at a time. If we have a positive charge, indeed the field lines will leave this positive charge and go outward. This is always the case, that the field lines leave that positive charge. So they're beginning at the positive charge, and then the arrows are showing that they leave that positive charge. And then negative charges, the field lines do go into it. So they are ending. So the arrows are pointing in toward it, meaning that they're sort of ending there. And I'll just connect these. So if these two charges were in the same world, then you'd have the field lines going from. And don't worry too much about the colors here. Just was sort of showing the positive and negative charges, blue and red respectively. But so those field lines, start at the positive, end at the negative. Now the second question is, this one is true. It's not incorrect. B, the density of field lines indicates the magnitude of the electric field. So if, for example, this one is 1 coulomb, and then we had another one which is negative, right? So this is like a 2 coulomb charge. Then in order to show the electric fields, we actually would just do more electric fields pointing in toward this. So this is true. So anytime you have, a bigger charge, that's going to cause a bigger electric field. So I'm saying we have a bigger charge, that causes a bigger electric field, and you can denote that in your picture with a higher density of field lines. So more field lines here, more density of field lines than here, because there's a bigger electric field around this bigger charge. So again, that is not incorrect. Now, C, field lines may cross. So let's say we went and we took a charge and we put it right here. Which way would that positive charge move? Well, earlier we said that the electric force is equal to Q, the size of that charge, times the electric field at that point. So we know that this positive charge is going to move to the right here along that field line, right? It's just because it's going to be forced in the same direction as that electric field. And the positive charge is just saying, how much is that force? But it's going to be forced in that direction. But if we also had a field line going, say, this way, we had the field lines cross, then we have this point right here where that charge, if it were right there, it would have no idea which direction to go, because one line is saying, okay, that charge should move to the right. This field line is saying that charge should move up, and the fields would have no idea where to go. It needs to know where to go. You can't have that. The force has to be well defined for any charge, so they cannot cross. So the answer for this one is indeed that C here is incorrect. A and B are correct. Okay, true or false? Coulomb's law, as it is usually written, which is K, that constant, then Q1, Q2 over R squared, and I've written that down here as well. This is sort of, typed out, but that same thing here, may always be used to find the force on charged objects no matter the shape, right? So basically this is saying, like, if we have, one charged object where this one has a, bunch of charge all around it, and the overall charge on this thing is Q1, and then we have some other object over here, and its charge is Q2, then if we wanted to know what the force was between these two, we could use this equation, right? So true or false, can we do that? So this is false. We can only use this equation right here in this form if we have point charges. So if these two are point charges, so this is Q1 and this is Q2, and they're at 2 points, and the distance between these 2 points is R, which is like our R squared in the denominator there, then we can find the force on charged 1 given by charge 2, use by this, or the force on charge 2 from charge 1 using this equation. But you couldn't do it over here. And one easy way to see that is like, what is R, right? So like, R from here to there is different from R from here to down there. So there isn't a well-defined single R, so you can't just simply use this equation. Now on to a bit of a longer problem here. So the situation we have is 3 identical point charges are shown below. So we have these 3 identical point charges. And so what is the electric field at the indicated point, this point down here, saying there's a distance r down here. I'm actually going to, just for convenience, I'm just going to call this distance d, because I'm going to use r a lot in writing out the answer. So let's say it's a distance d away. So this is, let me also correct it in the problem statement there. You can still use R, but it's just, I think it's a little bit cleaner to use D. Okay, so what is the, so we're being asked, what's the electric field at that point? And what is the force on an electron if we put an electron down here? And I'll just draw a little electron down here. Negative electron. But first, we're going to consider the situation where we just want to know what the electric field is right here before we actually put the electron down there. So let me first give you the equations, and then I encourage you, of course, to do this on your own, because it is just so much more boring listening to me. If you're just doing it on your own, then that's like super fun. But and it's probably faster, honestly, if you just do it on your own, and then you can just check my answer and be like, oh, well, I got it. So, but I'll give you a couple equations, right? So first, the electric field from a point charge to anywhere in space is equal to K, which is just a constant. Q, I'll do a capital Q, which is the charge of that point charge. Could be positive or negative. Here, all of ours are positive. Over r squared, and then we have an r hat, and this just means, like, if we have some point charge, I'll just draw a point charge here. If we're then considering like a point over here, like right up here like this, then the r hat is just saying, all right, draw a line between these two. And the electric field is the r hat is basically saying it's like along that line, like it's basically like a unit vector pointing in that direction right there. I'll also note you could, if you want to, write this as K Q over r squared, and the r hat you could always write as the vector r. So really the entire vector to that point, so this whole vector right here, divided by the magnitude of that vector r, which is just another r, or I'm just simplifying this a little bit, kq, like r vector over r cubed. And so this is just like, you can just write your electric field like that if you wish. Sometimes it's easier to write it like that. And then the second equation I'll give you, which you've seen before earlier in this, is just the electric force. Electric force is equal to Q, which is like, this Q is like our test charge Q, which for us is going to be an electron. So why don't we put that Q in red, because it's going to be an electron for us, and then times E. And so once we have E, it'll be easy to get the electric force. Okay, so go try that out, and then come on back here. Okay, welcome back. I'm happy to have you back here with me. So let's start off by calculating the electric field from just this one charge to right here. So what is the electric field from just that center one? And so I'm going to just denote each of these by an E and then a label. So I'm going to call E sub C the electric field center, and this is the electric field at this point D below that charge right there. And this one should be the easiest one to calculate of all of these, right? We have our equation K Q. I'm writing capital Q because I'm saying I don't know what it is yet, and then I'm going to use this R cubed. So our R cubed. So I'll just write the whole thing out. R cubed, and then the R vector, where the R is going to be that vector from this charge up here, right there, down to here. So that's going to be our R for this one, and so okay, so yeah, so this is basically like I'm trying to think. Should I put a coordinate system? I probably should, right? So let me put a coordinate system where we have x and y here like this. For our vectors, we care more about the direction they're pointing than exactly where the origin is. So for example, for this one, we have our r is going to be like this. So we have this is going to be a vector that is in the x direction, not going anywhere, right? We don't have this point left or right, so there's no x component to that as a vector. And then we have minus d as the y component of that particular vector, that spatial vector, right? So that I'm just writing this right here. And so if we write this out in our equation, we're going to have equal to k and q. So here we have that positive q, that charge, that was this right here, right up there, over, and then our r cubed, right? So this r down here, this is the distance of the vector, the magnitude of this vector here, which is just, it only has one component, and we can just see the length of it is just d, right? So that is just going to be d cubed, and then times our r vector, which is going to be 0, comma, negative d, or if you want to write this in unit vector notation, you could write this as minus k. The minus is from that minus d right there. And then we have d in the numerator and 2 d's in the denominator. So we're just, 3 d's, d cubed in the denominator. So that'll give us just a d cubed overall in the denominator. And then we have a positive q. I'll just write as q. Right there. And so this is going to, and then, right, I said we're going to do it in unit vector. So this is going to be y hat. So it's in the negative y hat direction. So this charge, which, positive charges, all electric fields point outward, and one outward direction is going to be this downward direction. And so this is going to be in the negative y hat direction, and the magnitude of it is q over d. So that's the electric field from one of these charges. Now, we need to find what the electric field is at this point from all three charges added together. So we can find, so now let's think about the other ones. All right, so I took a little pause to redraw the diagram over here just because I didn't want it getting too cluttered up there at the top. So just so you can sort of orient you, we have our previous work up there. I redrew it down here for you. Because I'll do some drawing on it, and then I rewrote our equation for electric field. This is the electric field from a point charge, and it's at the vector r away from that point charge. So we did this for our charge that was in the middle, and we're looking at the point down here. So our vector was from that point charge down to there. But now let's do it for the left point charge right here. So for our left point charge, to calculate the electric field, let's draw our vector. So here is our vector r for that particular case. And I'm going to say the electric field is going to be E, and it's from the left charge, so I'm just going to call it E sub L. And that is going to be equal to K. Again, we have like a positive Q. And then the distance that of this vector here, so right, so our r cubed down here, this is the distance of the vector from that point charge, right, from our point charge to the point we're considering right here, is going to be the magnitude, right? It's the magnitude of that vector. Okay, so what is the magnitude of that vector? Well, the magnitude of that vector is going to be, and so I'm just writing out what is r, the magnitude here. It's going to be Pythagorean theorem. It's just going to be d squared plus L over 2 squared, right? This is just, and the square root, just Pythagorean theorem. So this is, I'm just writing r, right? So I did our y squared plus x squared. Or you could do x, could have done x squared plus y squared. That would have been fine too. Same thing. And so we have now r in the denominator, but we have r cubed. So this is actually going to be a denominator where we sort of cube this r right there. So that magnitude is in parentheses, and then we have cubed it. And then our r vector here is going to be down d, so in the y direction, it's going to be minus d. So I'll write our vector again. I'll do it in unit vector form. So we'll have a minus d y hat, right? So this is right. This because this has like the y component of that vector is minus d, and then we have the vector goes to the right, L over 2, so this is going to be plus L over 2, because to the right is positive y x hat, like that. And then if we want to now find what is the electric field from that right charge, so from the charge over here on the right, then we need to now do the same thing, but consider the vector like this, which you'll notice has this length right here is the same as that length right there. But the only difference here is that the x component is now to the left there, so that's the negative x direction. And again, it's down, so we have the y component of that particular vector is going to be in the negative y direction as well. So everything is the same here, right? So if the electric field at that point, that is d down, right? So at this point down here, the electric field from this charge is going to be equal to, again, k, q. The length of those two vectors are the same, right? The length of this vector and this vector are the same. So again, we'll have this magnitude down here cubed. So this is going to, again, be square root of d squared. This is y, the y component of the vector squared, plus x squared. And then that is going to be plus our L over 2, which is our x squared. So that this is our r to the third power, y squared plus x squared, but you could have done, I mean, this is our x squared plus y squared right there. And then the vector, so essentially our r is, so for this one, it looked like this. The only difference between this vector and this vector is that our x component is positive for this one, and the x component is negative for that one. So our vector is going to look very similar, except for this sign right there. And so this vector is going to be minus d y hat minus L over 2 x hat. And now what we have is we have the electric field at this point from the right charge, we have the electric field from the left charge, like at this point, and then we also have the electric field right here from that center charge, and we just need to add them together to get the electric field at that point. So let's just add them together. Can't be too tough. So we have E total is going to be equal to, so let's see what all of these have in common. So all of these have in common a K, they all have a Q, and what else do they have in common? Well, let's just pull out the K and the Q for now. So K, Q, and then we have, from our central charge, we have 1 over d y hat. That's the entire thing there. Oh, we have a negative sign too. And then for our charge from the left, so this equation right here, let's write that out. And you know what I'm going to do? I'm going to, since the next two terms have the same denominator, just so we don't have to write this denominator twice, I'm going to write it just once. And then I'm just going to pull it out of the entire equation for those two. So this is going to be 1 over that square root of d squared plus L squared over 4, right? I just squared each of those. Cubed, there's the same thing as before, just made that square happen. Okay, and then this is actually times both of these terms. So this is just going to be, so now I'm just going to be adding this vector and this vector, which are both multiplied by this denominator, right? Same denominator, k and q, because they both have k and q. So we have just minus dy hat from the left charge plus L over 2x hat. And then from this, we have minus dy hat plus, oh, not plus, right? This is important, minus L over 2x hat. And then let's close our parentheses and then also close our big bracket there, because this whole thing's times k and q. And one nice thing you'll notice is that this term and this term cancel. And we actually are going to, oh, and you know what, I apologize if you caught this. I did forget this is actually a d squared right there. Okay, so now we're good. So now let's simplify this just a little bit. This is going to be equal to k, q, and then we have minus 1 over d squared. And oh, let's put this y hat out front too. So we also have our y hat. So we're in the y hat direction there. And then this is going to be plus 1 over, and then I'm going to put our square root and the cube together. You can just write that entire thing as d squared plus L squared over 4, and this whole thing can be 3 seconds power. That's the square root and the cube together, which is fine. It's just the same thing written differently. And then we have a d, and also we have a, so there's a y hat from both of these, but we have this y hat out here like this. But then they also both did have a minus sign. So let's put in that minus sign, minus like that. And this is our entire expression for the total electric field, which is in the negative y hat direction, which sort of makes sense because if you notice, you have a bunch of positive charges up here. The field lines are going to point downward away from them. And so right here, we have an electric field that's downward. Now, the last thing that we have to do is just remember the question asked also what's the force on an electron placed at that point. Well, if you remember, we had this equation right here. So all you have to do to get the force on an electron is take that electric field that we got down below and multiply it by the charge of an electron, which let me just give you that charge of an electron. So charge of an electron is going to be equal to minus 1.6 times 10 to the minus 19th coulombs, and just multiply that particular charge by this electric field, and that's going to be the force. And one thing you'll notice is that this is a negative charge. This is going to be in the negative y direction, right? This electric field was going to be pointing downward, but the resulting force on the electric charge on that electron, you're going to have that negative sign from this Q and the negative sign from this electric field pointing downward at our point right here, cancel each other to get a positive force, so in the positive y direction, which means that our negative electron will be pushed upward or attracted to these positive charges. Okay, our last couple questions here are asking us to think about that situation from the previous problem, but now instead of the 3-point charges, let's replace that with an infinite line of charge. So here is our infinite line. That's why it's going all the way across the page there. It goes all the way to the left, all the way to the right, and it has a positive charge per unit length. So for any given length here, there's a certain amount of charge. And we're just gonna, this is like, so lambda is basically, it's like 5 coulombs per every meter or something like that. So lambda is basically like coulombs per meter. So how many positive charges per unit length? But we're just gonna call that lambda. And so we're being asked to use Coulomb's law, essentially Coulomb's law, you'll see what I mean, to find the electric field at the point indicated. Again, we have this point that's a distance d down from, we had sort of like 3 charges before, but now we have a line of charge. So distance d down, and let me correct, let me put that d, make this r, I like it as d. A distance d from the central charge, meaning just from this center point here. Before that was our central charge. And then we, again, want to ask the same question, like, what about an electron placed at that point? And I will note that there's a hint, which is you only need to set up the integral. We're just going to set up the integral because the point of 2 is to show you mainly that there is a better way, which we'll do in part 3. So this is tough just to think about. Like, how do we possibly find the electric fields here from a line charge when we only have this equation over here? So I rewrote this equation as the electric field from a point charge, a vector r away, and that r has a magnitude of, r without the little vector sign above it. So how do we figure out what the electric field is right here? So I think the best way to think about what the electric field from a line charge is by just choosing a little segment right here of the line charge and think about using this equation for it. So, as we do in calculus, and I promise this will be a very, very straightforward way to use calculus, but like we usually just think of a small little piece of something. We usually call it like dq. So instead of a charge q, let's just say dq. And the d is just saying it's small. That's the only thing that matters. It's dq. And then the vector from that little dq down to the point that we're considering is our r vector. Now, since it's a little tiny small charge, it's only going to create a very little small amount of electric field down here. So the electric field that creates is, you could say, it's dE. So what I'm going to do is I'm just going to rewrite our point charge equation and say, the little bit of electric field that we get from that little piece of charge is just going to be K dq. So I'm just replacing Q with dq. And then we still have that it is that R away. So our R doesn't really change. And then if we want to find the electric field, all we have to do is do that integral right there, right? So let me just write this as an integral. So I'm going to bring it over here to the left-hand side. So the integral of dE is equal to the integral of k, and we have our r vector. Let's zoom in a little bit. R cubed, and then dq. Now, this thing right here, we can just write that. So we're just, that's just the integration over all of the electric field to give us the total electric field. So we can just call this E. So the electric field is going to just be this integral over dq. Now, the only real trick here, the only real tricky thing we have to do is figure out what the heck is dq, right? Like, what is this dq thing? Well, remember, lambda is going to be equal to, let's say for any part of this, like any part of this line charge, like let's say we just consider some like delta x over here. So let's just say like this right here, from here to right there, like this thing. Let's just call this like, I don't know, just some delta x distance. Then there's going to be some amount of q in that delta x distance. Or you might say that this is like a very small distance, and you could just say like, oh no, let's just call it like dx, or some dx distance. And oh wait, that's kind of like over here we have some little d, like there's some very small distance that was covering. So what I'm trying to essentially point out here is, like, if you look at this little thing right here, then the amount of charge per unit length you could think of as dq over dx. And if we rearrange that, we get that dq is equal to lambda dx. And so we can rewrite our equation over here as the integral, and the k can come out, the k is a constant, of r cubed, and then this dq can be lambda dx. And we've done this before, right? I mean, essentially, we've written out this exact same equation in the previous problem. I'm just going to take the k, and remember, lambda is constant, so I'll take the lambda out of the integral too. The integral is just going to be, and we can think of it. I know it's hard because it's in the integral, so it's a little bit scary, but you can just think about this particular vector here for this particular dq. If we just think about the x component, which here is going to be, I don't know, you could just pretty much call this x. You don't have to, we don't, right? Before, this vector was L over 2. In this case, we can just call this vector minus x, right? You could just say, this that we have, this is essentially like a distance x away, and then the x component here is just, you just call it x, let it vary. It'll be fine, let it vary. So our r vector is going to be minus x in our x hat direction, And then our y, right? So also we'll have like a y component here, which is going to be like minus d in the y-hat direction. And we have the same denominator we had in the previous problem, which is going to be d squared. And before we had L over 2, now all we have is x squared because our x component of that vector is not L over 2. It is x, or negative x, but we squared it. And then that was to the 3/2 power. And then we have dx. Now, we set up the integral. So based on what we were asked to do, what we were asked to do up here is we just needed to set up the integral. And so that is good. We are done. The whole point of this entire thing is just to say there has got to be a better way than doing this integral. And if you ever actually had to do this integral on an exam or something, you would totally be given the integral here. So I just don't worry about that. Don't worry about doing this integral. If you want to, you can, and then confirm that you get the same answer as we get in this next part of the problem. But the next part of the problem is saying repeat the calculation except use Gauss's law, which is going to be so much easier. So again, what we have is we have our line charge. So this is our line charge with all of our little pluses on it. So it's the exact same one as above. Assume that the pluses are equally spaced because it's a uniform lambda charge, right? So the same amount of charge per distance in that x direction that we care about. And then, okay, how does Gauss's law work? So Gauss's law works like this. We just want to think, what do we know about the electric field based on this line of charge? And can we use the symmetry of that to figure out our answer? So what I'm going to do is I want to sort of consider what is the direction of the electric charge coming off of this. So let's just remember one thing, and that's from earlier. We noticed that for any positive charge, the field lines point outward, right? So this was from earlier. The field lines begin at positive charges and end at negative charges. But you could also imagine this sort of thing as it's hard to draw, but imagine if we were just like sort of looking at our line charge head on. So, if our eye was over here and we were looking sort of looking head on at this, we would see that all the electric field lines are pointing outward because we're sort of looking along a positive charge. Or another way to say that is that we would have electric fields pointing up over here away from that positive charge line downward here. And all along it, we would have this, positive, the electric field up on the top, electric field down on the bottom. And so we just know sort of from looking at a charge the direction of the electric field. You can also do this through symmetry. So basically, if you were like, no, I could totally imagine having a charge that's pointing this direction. Why not, right? Well, then what I would say to you is I would say, well, you have the same amount of positive charge on the left and the same amount of positive charge here on the right. So why would you have any electric field that's pointing toward one and not toward the other direction? Like the charges on the left and the right are symmetric. So why would you have an electric field that like favors one side essentially? So you can't have that, right? You can't have your electric field pointing to one side when it's symmetric left to right. All right, so here is the magical part. The magical part is drawing a Gaussian surface that aligns with the symmetry of the charge. Meaning, like, we have this line charge, And a Gaussian surface is supposed to go around our charges. So why don't we draw a Gaussian surface that's a cylinder that goes perfectly around this. I'm just going to make it length L, and its radius is let's call it capital R. You can make these up. It's totally fine. All right, what are we going to do with this Gaussian surface? Well, again, let's look back over here where we were looking at that line of charge just head on, our eye looking head on. Well, our Gaussian surface, when we look head on too, is going to be this circle. So sorry, my drawing is not perfect. But one thing that you'll notice is that if this were drawn a little bit better, that the electric field is perpendicular to the surface, right? Right here, it's perpendicular to the surface. Here, perpendicular to the surface. All right, so right now, what I'm going to try to do is I'm going to try to draw our cylinder a little bit like this, just so you can sort of see the length of it. So one thing you'll notice is that if I were to draw a little piece of the area of our Gaussian surface, then it has an area vector that is perpendicular to the surface as well, right? So we have our area vector here, and also our electric field was perpendicular to the surface. So that means that the area vector is actually parallel to the electric field vector. And that's actually going to be true not just right here, but right here too, and actually everywhere along this Gaussian surface, just based on us drawing it in a way, right? A cylinder is respecting essentially the symmetry of this line, because a line, move it to the left or the right, it looks the same. Cylinder, move it to the left or right, it pretty much looks the same. And so just by doing that, we've set it up in a way such that the area of the curved part of the cylinder is always going to be at any given point completely parallel. So the area vector is going to be parallel to the electric field at that point. So we'll use that fact in just 1 second. All right, so now let's write the equation out for Gauss's law, which honestly is my favorite law. So the flux is equal to the surface integral, meaning the integral over that entire Gaussian surface, of the electric field dotted into the area. So for every little area, we're going to do a dot product with the electric field there. And that's going to be equal to the charge enclosed in the Gaussian surface over epsilon naught, which is just a constant. Okay, so this looks a little bit intimidating, right? This integral looks a little bit intimidating, but I promise you it's actually quite easy. So let's break this up into two integrals, one for the integral for the end caps, like this part and this part, and then one for the curved part of it. So let's just do that quickly, and just by notation. It's not just, I'm just going to write pretty much what I said in words, which is we're going to do the integral of E dot dA, but the area here we just care about is like the end caps. And then we'll do plus an integral. I'm not saying surface integral because these are two different pieces. They're not the whole closed surface on their own. So E dot dA, and then this is like the curved part of it, is equal to that Q enclosed over epsilon naught. Now, one thing to notice is that the electric field, remember the electric field is like this. It's actually going to be at the end caps, it's going to be the electric field is parallel to the end cap surface. Or another way to say it is that the surface of the end cap has an area vector that's like this. which is perpendicular to the electric field vector. And what that means for us is that for the electric field right here and the area vector there, they're 90 degrees to each other. So the dot product of two things that are 90 degrees to each other is 0. So we don't have to worry about that at all. Now, the dot product for this one, we said earlier that all of the area vectors are going to be completely parallel, right? So like if we just go back up over here, we had the area vector was parallel to the electric field vector. So what that means is that this dot product between E and dA, if those are parallel, that means the angle between them is going to be 0. And so this we can just write as the integral of the magnitude of E times the magnitude of dA times the cosine of theta between them. Theta is 0, so it's actually going to be 1. So you can just, this is just E times dA. The dot product goes away. It's just 1 here. And that is equal to Q enclosed over epsilon naught. And one, again, very cool thing here is that the electric field for our particular Gaussian surface, the electric field is actually going to be the same magnitude because we put our cylinder exactly around this. So there's no reason why the electric field, like say up here, would be different than right there, because you could imagine looking at the thing upside down and it would look identical, right? Or you could flip the whole thing, spin the whole thing around the radius, like, spin it around like, some angle theta, and everything would look the same. So basically what I'm trying to say is that there's cylindrical symmetry here, and that means that the electric field everywhere on the curved part of the surface, the electric field is going to be the exact same magnitude. And so that's sort of thing that if you just sort of think about the symmetry, you can convince yourself of too. So here we can pull our electric field out of the integral of dA. So we just are integrating over that total area is equal to Q enclosed over epsilon naught. And then our total area of a cylinder, so it's just the area of the cylinder. So the electric field times the area of the cylinder, which is 2 pi r L. So this is the circumference times the length of it. And then Q enclosed is going to be lambda times L, because so we have the amount that is enclosed here is just this part, like so from right here to right there. So this is going to be length L of that charge, and it has a density lambda, which is essentially going to be charge per unit length. And so if we multiply lambda times the length, we'll get the charge. And that's all I've done right here. So I did lambda times the length equals that charge enclosed Q. That is over epsilon naught. And you can notice that we have two L's, so those L's can cancel. And then we just know that the magnitude of the electric field is going to equal lambda over 2 pi r, which is the distance away from that line of charge, epsilon naught. And then this is, I think, an easier way to do it than doing our crazy integral over here, right? Essentially, what this equation says is it says the magnitude of the electric field is going to be this. And based on the little pictures that we drew earlier, we know that, right? So we know, like, essentially from this picture that we drew here and from this picture we drew here, that the electric field is radially outward. So it's this magnitude, and the direction is going to be radially outward, cylindrically. So I hope that was helpful in clarifying a bit about Gauss's law and some of the other concepts. And have a great day.